Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video that you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present Glycidyl Ester ether epoxy systems. The aim of today's talk is to distinguish between Glycidyl Ester and Glycidyl Ester epoxy systems. Previously, various classification methods were introduced to classify epoxy system. One can classify epoxy system based on their physical states into solids, semi-solids or liquids or solutions resins. Another way to classify epoxy resins is based on their applications. Similarly, one can consider the chemical structure of the backbone of epoxy resins and classify them into aromatic and aliphatic resins. Another way to classify these resins is to consider the Glycidyl group. It has been mentioned earlier that a chemical structure with an oxygen ring is classified as an epoxy. The epoxy system then can be divided into glycidyl and non-glycidyl systems. The one which have glycidyl groups and the one with no glycidyl groups in them. The glycidyl epoxies then can be subcategorized into different groups, for example, glycidyl ethers, glycidyl esters, and glycidyl amines, which will be discussed later in this video in more detail. For now, let us focus on the glycidyl group. If we recognize this group in an epoxy structure, we can put the epoxy in the glycidyl-based epoxy groups. Starting from scratch, let us recall the oxygen ring or the epoxy groups. Here you can see a schematic of an oxygen ring. The term epoxy is used to describe a range of monomers containing an epoxy group, while epoxy resins refers to a class of molecules containing at least two epoxy groups. Examples of widely used epoxy monomers have been presented here, and epoxide group have been highlighted in each case. There are several ways to introduce this epoxy group into the system. One way is to use peroxide acids in the reaction. Another way is to employ epichlorohydrin in the synthesis of epoxy resins. The structure of ECH has been presented here for your reference. In the synthesis of bisphenol A or F epoxy resins, for example, epichlorohydrin is reacted with bisphenol A or bisphenol F and chlorine is released as NaCl. Therefore, in these cases, the source of the epoxide ring in the final product would be epichlorohydrin. There are several ways that this epoxide ring can be attached to the structure, but let's first introduce glycidyl group. A schematic of glycidyl functional group has been presented here. Glycidyl group is a functional group having an epoxy ring attached to a methyl group. The reactivity of this functional group is at the carbon atom of the methyl group. One hydrogen atom is eliminated from the methyl group, forming a vacant point for another chemical moiety. Therefore, whenever the chemical component possesses this group in its structure, it is called a glycidyl epoxy resin. If we have two glycidyl groups in the structure, it is called diglycidyl epoxy resin. If we have four of them, then it is called a tetraglycidyl epoxy resin. There are also cases which we have a structure with epoxy resins where glycidyl groups are not present. These types of epoxies are called non-glycidyl epoxy resins. In the presented schematic here, the bottom two epoxy resins are not glycidyl epoxy resins. Often non-glycidyl epoxy resins are divided into cycloaliphatics and aliphatic epoxies. Now that we have introduced the glycidyl group, we should mention that there are several ways that this glycidyl group can be attached to the backbone of the chemical. Before introducing the possible ways of attaching this functional group into the component, we should introduce different functional groups in the linkages. Ether linkage or ether bond is the first group we must be able to recognize. A functional group characterized by an oxygen atom single bonded to two carbon atoms is called an ether. The carbon atoms may be of any hybridization but cannot be carbonyl groups. In the ether, the oxygen must be bounded to carbon on both sides. If one of the R groups is a hydrogen atom, then the compound is alcohol. Therefore, the structure is an oxygen single bonded to two alkyl groups. The formula is ROR prime. Their atomic weight is bigger than 46 grams per mole, and they are generally basic. Ether can act as a Lewis base because of the lone pair of oxygen that they have. The ether linkage of glycidyl has been presented here. Ester functional group. The basic structure of an ester consists of a carbon single bonded to carbon, double bonded to oxygen, and a single bonded to oxygen. The simple structure of an ester has been presented here for your reference. The basic chemical formula of an ester is R bonded to COOR prime. The R groups denoted the rest of the molecule not included in the functional group. Fischer esterification is the most common reaction to make simple esters and involve mixing a carboxylic acid and an alcohol with a small amount of catalytic acid. The main difference between ether and ester lies in their structure. An ester group requires two oxygen atoms and two carbon atoms to complete its characteristic structure, while an ether group only needs one oxygen atom and two carbon atoms for its structure. Compared to ethers, the melting and boiling point of esters are higher. It should be also mentioned that unlike ethers, where no pi bonds are involved, in the esters pi bonds or double bonds exist between C and O. Also, the ester bond give a polar nature to the finished component, whereas ethers and ethers linkages are non-polar. Therefore, an epoxy with an steric linkage is much more polar than the one with an etheric linkage. The schematic of an epoxy with steric linkage has been presented here. The third way to link a glycidyl functional group to a component is to employ an amine link. Here in the N is the core of the linkage. From one side it has been linked to the glycidyl group, and from one side it has been attached to the main structure. And the third side can be used for another functional group or another glycidyl group. A typical glycidyl amine has shown here for your reference. As discussed earlier, when glycidyl groups are attached to the structure through an ether bond ROR prime, we have a glycidyl ether epoxy. Based on the structure of the epoxy, glycidyl ether resins can be classified into three main categories, including aromatics, aliphatics, and cycloaliphatics. As the nomenclature indicates, in aromatic glycidyl ether system, at least one aromatic ring is present. Examples of aromatic glycidyl ether epoxies are the famous diglycidyl ether bisphenol A, diglycidyl ether bisphenol F, and Novolac epoxy resins. The term ether in their name implies the presence of the etheric link. Therefore, whenever the glycidyl group through etheric linkage is detected and there were aromatic rings, it is an aromatic glycidyl ether epoxy. Moreover, it should be mentioned that a structure with at least two epoxy groups can be considered as epoxies. However, systems with one epoxide ring are technically considered reactive diluents. The reactive diluent is a low viscosity resin that is often used to reduce or modify the viscosity of epoxy. Due to the presence of epoxy rings in their structure, they are epoxy systems. However, reactive diluents will be discussed in a separate video. To this end, two things should be noticed. Firstly, there are systems with one epoxide rings, often with much lower viscosities, which are used as the diluents to reduce the viscosity of epoxy resins, and simply other type of epoxies. And secondly, the choice of the reactive diluent for an epoxy system is dependent on the chemical structures of the diluent and the main epoxy. Therefore, aromatic diluents are suitable for aromatic epoxies. There is also a possibility of the presence of more epoxide groups in the molecular structure, which result in simply epoxies with more active epoxy sites, consequently resulting in higher cross-linking density and improved mechanical properties of the cured product. Therefore, we have mono, di, and multi-glycidyl components. In the Glycidyl Ester bisphenol A epoxy resin, for example, the D letter indicates that there are two glycidyl groups are involved. For aliphatic, we do not have aromaticity, and also there are no cyclic groups. These epoxy systems can have unsaturated groups in them. However, they do not possess an aromatic ring or cyclic aromatic ring. Examples include butanediol diglycidyl ether with the first structure. A key use of this product is modifying the viscosity and properties of epoxy resin. So technically it can be considered as a reactive diluent. The use of the diluent does affect the mechanical properties and microstructure of epoxy resins, whereas it reduces the viscosity and increases the processability. Another example is 1,6-hexanediol diglycidyl ether. Similar to the former one, its main use is for the reduction of viscosity in epoxy resin systems. It is thus an epoxy reactive diluent. The chain length helps give more degree of flexibility to the epoxy. Castor oil 3-glycidyl ether is another example of this family with 3 epoxy groups. This product can be used as a modifier for epoxy resin as a reactive diluent that adds flexibility and improved mechanical properties to the base system. Finally, we have cycloaliphatic resins, which have glycidyl ether groups in their structures. The number of available glycidyl ether groups can be 1, 2, or more. In this case, the component contains rings, but they are not aromatic. Example includes hydrogenated bisphenol A epoxy resins, which is commercially produced by the hydrogenation of ordinary bisphenol A epoxy resins. The structure of these epoxy resins has been presented here. The viscosity of this type of resin is in the range of 1,800 to 2,500 centipoise at 25 centigrade, and its EEW is 210 to 220 gram per equivalent. This epoxy resin is suitable for coatings, constructions, and composites. Another commercial example of this class is cyclohexane dimethanol diglycidyl ether. This is a difunctional reactive diluent or intermediate for the synthesis of cycloaliphatic resins for application where improved outdoor resistance is needed. The viscosity of this product at 25 centigrade is in the range of 55 to 75 centipoise, and its EEW is 155 to 165 gram per equivalent. The linkage between the glycidyl group and the rest of the molecule can be of esteric type. Unlike the ether linkage in which alcohols are involved, in the case of ester linkage, carboxylic acid are involved. In other words, glycidyl esters are produced by the reaction between mono or dicarboxylic acid and epichlorohydrin, followed by dehydrohalogenation and in the final structure R prime functional group can be seen. One of the R groups would be the glycidyl group. The schematic of the reaction has been presented here. Regarding the synthesis, glycidyl esters are produced by the reaction between mono or dicarboxylic acid and epichlorohydrin, followed by dehydrohalogenation. If the carboxylic acid are employed, the glycidyl ester structures are produced. The reaction is often done in the presence of an alkali, for example, sodium hydroxide. Resultant resins can be monofunctional, difunctional, or even with higher functionality, depending on the starting material. These resins are typically more polar than glycidyl ethers and display low viscosity at room temperature, for example 500 millipascal/second. But they have similar reactivity to bisphenol A epoxy resins. These features mean that they can be used as reactive diluents used to modify and reduce the viscosity of other epoxy resins. 1,2-cyclohexane dicarboxylic acid diglycidyl ester is one of the most well-known diglycidyl esters in the market. It is used as a high-temperature resistance coating for substrates such as metal and plastics. This product has been shown to be resistant to water vapor and the formation of hydroperoxides and peroxides, which can lead to degradation of the coating. Cardura E10P of Hexion is a neodycanoic acid glycidyl ester with a viscosity of 5 to 10 centipoise at 25 centigrades and EEW of 235 to 244. It is a versatile reactive modifier that provides good moisture resistance while lowering the viscosity of an epoxy system. It helps to decrease the tendency of the epoxy resins to crystal as well. Adipic acid diglycidyl ester is another example of this class and can be used to produce high-grade alkyd resins, polyester resins, acrylic resins, and also it can be used as epoxy diluent. Mainly it is used in coatings, paints, and dyes, and so on. Many of cycloaliphatic epoxy systems are of this type. Glycidyl amine-based epoxies. Herein again we are dealing with an epoxy structure with epoxide groups containing glycidyl groups, where the linkage between the glycidyl and the molecule is an amine linkage. We can identify the glycidyl group which has been connected to the rest of the molecule through an amine link. Glycidyl amine epoxy resins, or GAER, are produced by the reaction of aromatic amines with epichlorohydrin. Two typical glycidyl amine epoxy resins are 3-glycidyl para-aminophenol and 3-glycidyl of 4,4-aminophenoxyphenol. These highly reactive resins, when fully cross-linked, possess high thermal and chemical resistance, a high glass temperature, and heat deflection temperature, and outstanding mechanical properties. They also possess a lower room temperature viscosity compared to standard epoxy, which facilitates handling and processing. Here the schematic of these resins has been presented. Sometimes the terms tetraglycidyl amine epoxies and 3-glycidyl amine resins are used instead of the whole name. Technically, these names imply resins with 4 and 3 epoxide groups respectively. As the functionality increases, the cross-linking density would be higher and therefore the mechanical performance of the cured product significantly improved. Regarding the advantages and disadvantages associated with these systems, we should imply that due to their outstanding thermal stability, good adhesion strength, and low viscosity, glycidyl amine epoxy resins are increasingly used in the manufacture of high-performance composites, adhesives, and coatings, and find several applications in the aerospace and aircraft industries. However, fully cross-linked glycidyl amine epoxy resins are rather brittle, which limits their application when higher impact strength is required. To improve their toughness, GAAs are blended with thermoplastic resins such as polyether sulfone, polyterephthalic imides and polyether ketones. Due to their low viscosity, they can also be used as reactive diluents for more viscous engineering thermoplastics. In these resins, a great degree of cross-linkage results in high reactivity, high thermal resistance, high chemical resistance, high TG, outstanding mechanical properties, and relatively low room temperature viscosity for easy handling. Therefore, these resins are designed for manufacturing high-performance fiber-reinforced composites, adhesives, and coatings. Compared with the epoxy resins of diphenyl propane, Glycidyl Ester epoxy resin has a lower viscosity and better workability. High reaction activity. The adhesive force is higher than that of general epoxy resins, and the cured product has good mechanical properties, good electrical insulation, good weather resistance, excellent ultra-low temperature resistance, and a still higher bound strength than other types of epoxy resins under ultra-low temperature conditions. It has a good surface gloss, light transmittance, and weather resistance. And for application, Glycidyl Amine epoxy resin is a common resin matrix for high-performance composite, which is characterized by multifunction, low viscosity, high activity, etc. It is also suitable for glass fiber, carbon fiber composite materials for aerospace, such as airplanes and rockets, heat-resistant solvent-free coatings, electrical insulation materials like electrical insulating epoxy, heat-resistant adhesives, and other high-performance applications. The type of resin can be used in special property composites, special high-temperature resistant materials, and also for electric and electronic castables and other fields. Glycidyl amine insulation epoxy is suitable for special high-temperature resistant materials. And it can be used for high-temperature resistant adhesives. Glycidyl amine epoxy resins can also be used in electronic and electronic castables and other fields. Thanks for your attention. I hope you enjoy. Please share your thoughts, comments, or questions, and I will come back to you soon. Thank you.